Okay, here we are, Lecture 4, Manometry, a word that probably doesn't mean anything to you at this moment. But we're going to work with a whole bunch of different manometers, I guess is the word that and then what we're going to do with manometers is, basically a manometer is a fancy word. It's just a way to measure pressure. And there's a lot of different ways that they do these, particularly because sometimes you get really big pressures and you don't really want to deal with a really big manometer. But basically this is the way that we measured pressure before we had like a digital manometer. I would think that even the digital manometer is probably working on the same principles, but I'm not exactly sure how they work. But I do know how these work, and so I'm going to teach you. And one thing to note here, if you're like looking at this is really crucial. Manometers, they show up all the time. I make a point that there's a manometer on every single test that I've given. I may not have completely done that, but that was certainly the plan. Usually there's one manometer or two manometers on pretty much every single test. The first test, the problem is going to be just a manometer problem, like solve for the pressure in this system. But as you kind of get along, usually the manometer is just like an aside. Like the understanding, the expectation is that you can solve a manometer. This doesn't mean that all of my students can do this. So what I want to do is I want to emphasize that you work on this until it makes some sense. Okay, you just keep driving at it. Okay, so basically what I'm trying to say is these manometers are important. Okay, you have to learn this. This isn't something where you can kind of get halfway through it and go, I'm just going to miss that problem. It's going to show up all the way through the semester. It's going to show up constantly. Okay, one thing that I want to do before we kind of jump into what is a manometer and how do they work is the hydrostatic law. So we had this from last class, and it's really like this. So basically what this says, okay, dP dz, dz, is that the pressure increases as you move downwards in a fluid at a rate that is equal to, the pressure increases as you move downwards in a fluid at a rate equal to gamma, which is the specific weight. Okay, if gamma is constant, okay, then this becomes a lot easier. Okay, then we typically can say the change in pressure equals, as we move downwards in the fluid, equals gamma times the change in Z. Okay, so that's pretty, actually I guess there's a negative sign right here. Okay, so that's pretty nice. Okay, so so that means if I go from like height 1 to height 2 or whatever, okay, then my Z has changed, maybe I've gone down negative H or something, so I could plug that in to Z and my pressure would have increased by gamma H. Okay, so that's how this typically works. Okay, so I'm going to show you a few of these, and I think that this is going to make some sense. All right, so let's zoom down here. I've drawn some manometers, and I want to take a moment to kind of talk to you about these ridiculously terrible drawings that I've drawn. And obviously, my horrible, I don't know what happened right there. Anyway, so what we're looking at, let's look at this one on the right, okay? And I want to describe what a few things are going to show up in a lot of these drawings that are kind of, so first of all, I'm going to help you understand the drawings, and then we're going to talk about, simple manometers, okay? So the first thing that we want to know about, well, let me describe the drawing, and then I'll kind of talk about what the manometer is and what it's doing. So first of all, you see this little kind of squiggly thing right here. So we've got some kind of pipe here, and we've got these little squiggles that I drew. Any squiggles like that or like that on either end of a pipe, okay? What those are to show you is that the pipe basically continues. Pipe continues. Okay, so it's a way that it's kind of shown up in engineering, and people have needed to basically say, look, I can't draw the entire pipe. Okay, the pipe continues. I can't really draw it. So just accept the fact that the pipe keeps going, the water keeps going. I'm only drawing this portion of the pipe. Okay, and then this one right here. Okay, notice that it doesn't have that, and so what that means is that this bit right here is open to the atmosphere. Open to atmosphere. Okay, or whatever. The pipe ends right there. Okay, the other way that I might do this sometimes is I might do it like this. I might draw it like that. Okay, that means, well, you know what, for now, no. I'm going to make these open to the atmosphere for now. Eventually later in the class I might draw them like that, but we'll get to that distinction later. Okay, so that's kind of what you need to know. Okay, so the point of a manometer, if we just, kind of think about what is a manometer, and the manometer in this particular problem is that tube sticking up out of the larger tube. So this is a pipe. This whole thing is a pipe, and this is the manometer. Okay, and the point of the manometer is that it measures pressure. Now, how does it do that? Well, pretty straightforward in this case, and I think maybe you can imagine it. If you wanted to know the pressure at this point A, okay, and you were like, well, I'm gonna pop a little hole in my pipe, and then what's going to determine the pressure at A? Well, what's going to determine the pressure is going to be how far up the water goes in the smaller pipe. Okay, now based on what we've just done, you might say, well, what about surface tension? Because that's going to cause it to want to rise, with the capillary effect, and that doesn't really matter usually because it's a very small effect. As long as the manometer tube is wide enough, then the surface tension won't really matter. Okay. Anyway, so in this case, it's if the pressure at A is really high, you're going to expect this the water in this tube to go really is going to just shoot up really high. Okay, and if the pressure in the tube is not that high, then it won't go very high. So for example, in this problem, or in this example drawing thing here, if I wanted to know the pressure at A, okay, what is that? Okay, well, here's how we would do it. We would say, okay, well, what's the pressure? I'm going to call this pressure point B right here. Okay, and I want to compare the pressure at point B to point A. Okay, so the way we do that is I say, okay, well, the hydrostatic law was that, the third way that we wrote it was pressure at A over gamma plus the elevation at A equals the pressure at B divided by gamma plus the elevation of B. Okay, cool. So let's see. Well, what's the pressure at B? Well, it's atmospheric. Okay, so what I'm going to do here is what I always do is I'm going to make this 0 because I'm going to be working in gauge. Okay. All right, cool. Let's see. ZB is higher than ZA. So let's define the distance between those two. Okay, so let's define this distance between B and A. I'm going to call that H. Okay. And then now that I've got that distance, I can say, okay, well, ZB minus ZA, ZB minus ZA, if I bring that over to the right-hand side, okay, this is now defined as H. Okay. So then I can say that PA equals gamma times H. Okay, pretty easy. Okay. So, or at least it's a nice, pretty solution. I don't mean that it's easy to get to that, especially the first time you see it. But what it means is that, okay, so this pressure is in gauge. And so what this basically tells me is that the pressure at A is gamma times H higher than the pressure at B. Okay, and the pressure at B is 0. Now, if you wanted to, and you wanted to make the, if you wanted to do this in absolute, we could add the pressure at B. But instead of making it B, we could make it the pressure of the atmosphere. Okay, so this could either be 0 gauge, okay, my recommendation, or you could make it 101.325 kilopascals absolute. Okay, I think hopefully it's clear which one of these is easier and which one of these I recommend. Okay, so I recommend doing this one. All right, cool. All right, so let's go over to this other manometer. Okay, so this one's got a little twist in it. Okay, a turn in it. And basically we're going to do the exact same thing. Okay, so if I wanted to know the pressure right here at A, okay, some point A, it looks like plus A, but really it's just some location A. Well, then what I need to know here is just this height between these two things. Okay, because here's a point right here. Point well, I don't want to call it point B. Let's just call it B. Okay. So, and if I wanted to go between those 2 points, well, let's see, the pressure at A over gamma plus Z at A equals the pressure at B over gamma plus Z at B. Okay, and if I run through it, I'm gonna get the exact same solution I got last time. Okay, because it's gonna algebraically be step-by-step identical. So the pressure at A equals gamma times H. Okay. Now, what's interesting about this is there's a few things that are a little weird about this. Is that there's a kink here. And your inclination might be, well, that kink is somehow going to affect the pressure. And what I want to note here is that the hydrostatic pressure law, okay, if we go up here, okay, dP dz equals negative gamma. Okay, this says nothing about horizontal. Okay, dP dx, okay, for hydrostatic fluid equals 0 for hydrostatic fluid. Okay, so there is no horizontal variation in pressure in a static fluid. Okay, if the fluid is moving, then it is moving left. If it's moving left or right, it's precisely because dP dx does not equal 0. Okay, but for a hydrostatic fluid, there's no pressure gradient laterally. Okay, so the fluid will not flow to the left or the right. Okay, so basically, if I trace this, you know, the pressure here, the pressure is increasing as I go down into the fluid. Okay, and then it stays the same all along here. Okay, until we get to point A. Okay. If the pressure did not do that, then there would be flow from like here to A, or vice versa if there was a pressure difference. Okay, so that is the simplest of the manometer. The drawback to this, okay, and the reason that we use more complicated manometers is I want to imagine, what if the pressure at A were really, really, really high? Like, what if this pressure was really high? Well, then what's going to happen is it's going to drive the flow this way, or not the flow, but it's going to drive the water this way, and H will get really, really, really large. So if I look at this, if pressure is really, really high, then H is going to get massive. Okay, so we can end up with H like way up here. Okay, or we could, you know, quadruple or 10 times or whatever, and then you're in a lab or something, or you're in a plant or whatever, and you want to know the pressure inside your pipe or your vessel or whatever, but you've got a manometer now that's going up like, I don't know, 3 stories or something, you know, and so somebody on the 3rd story has to read it. Well, that's not going to be very useful, right? I mean, I guess it's still useful. It's just awfully inconvenient, right? And so you might say, okay, but Dr. Wagner, at least I kind of hope you're saying this, but what about that gamma? Couldn't we change the gamma? Well, you could change the gamma. You know, like what if you use mercury, then it's not going to push this13 quite as high. You know, mercury has a specific weight of 13.5. So mercury is only going to get pushed 13.6 as high as water. But the problem is, what if your tank has something other than mercury, right? Okay, so that's one, actually, you're kind of driving at, or at least I'm driving at, hopefully you're having the similar kind of thoughts, is that they deal with this doing 2 things typically. One is a U-tube, not YouTube like the channel, but they use U-tube manometers, and they use multiple fluids, okay? And we'll talk about both of those, multiple fluid manometers. Okay, so that's kind of how they deal with both of those, and we'll do those right now. So yeah. Okay, so before I move on, I want to note that this simple one with kind of the tube sticking up out of the side of a pipe, not that one. So son of a. So anyway, so if you have a simple pipe, you know, and you just, well, usually I've been drawing my pipes in white, but whatever. And we're like, I want to know what the pressure is, and you just kind of put a little tube on the side of it. Okay, this is a simple manometer called a piezometer. Okay, this is the simplest way to do it. I think probably in common use you can have people calling all kinds of different things piezometers, but anyway, so let's go talk over here about these U-tube manometers. Okay, so I'm going to zoom all the way in on this one, And I'm going to this is going to be the first time I talk through a quote-unquote complicated one. These can get a lot more complicated. I could draw one that you're just going to be sitting there all freaking day just figuring it out. But the rules kind of just keep going and going and going. So they're not, hopefully once you learn the rules, these become, if not, they're not more complicated, they're just longer. You're just going to keep doing the same thing again and again and again. All right, so if I wanted to know the pressure at A, okay, this is the first time I'm going to walk you through this, okay? And what I'm going to do basically is the pressure at A is somehow related to the pressure here. Okay, so what I'm going to do is I'm going to give you some distances here. So from A downwards to this point is going to be height H. Okay, and that's all I know at this point. Okay, so what I want to know, so what you can kind of think about if you look at this is you can see that if the pressure at A were really, really, really high, okay, if it were really, really high, then the fluid would move up, say maybe up here. Okay, if the fluid at A were the same as the pressure in the air, okay, I can tell you right now it would be right here. Okay, and in fact, we're going to end up with a negative pressure here because we're actually below that point. One thing that I want to note here, actually before I continue this problem, because I forget this, you guys don't look at these diagrams all that often, but this right here is a pipe. Okay, and this pipe is coming into or out of the board. Okay, and then the rest of this is just a tube off to the side of it. Okay, so whenever you see like a round circle, usually what they're showing you is a cross section of a pipe. Okay, so this is a cross section of a pipe. All right, so if I want to know what the pressure at A is, and I'm going to basically compare it to pressure at the only place where I know the pressure. Okay, and the only place I know the pressure is at that little dot that I wrote. Okay, so it's at this point, which, what do we want to call this point? Well, this point is like it's touching the atmosphere. So it has pressure atmosphere. So that's one way to do it. Let's see, I'm going to go ahead and I'm going to call it point C, just because I kind of have some ideas here of what I want to do. Okay, so let's call this point C. All right, so what I'm going to do is I'm going to walk from one point to another. Okay, and so we'll do that by, I'm going to start at C. Okay, I've actually done this incorrectly already because, I'm an idiot. Anyway, so I'm going to start at point C. This is how I do this every time. So I'm going to say to myself, all right, I'm going to go from point C downwards to another point right here, which I don't know what we're going to call that. Well, I didn't leave myself enough points. Let's just call it point D then. Okay, it doesn't really matter. All right, so the pressure at point C, if I add the change in pressure from point C to point D, then I'm going to get the pressure at point D. Okay, so this whole thing right here, this is the pressure at point D. Okay, now if I'm going to move through the fluid this way, okay, to a point E, okay, then basically I'm going to add the change in pressure from point D to point E. All right. Now, okay, so now I've got the pressure at point E. So if I do all of this, I've got the pressure at point E. Okay, so then I'm going to go from point E and I'm going to go upwards. Well, we're going to do this in two steps, actually. Let's go ahead and undo that. Okay, and so let's do, we're going to go from point E up until we're like even with point C. So this is going to be point F. Okay, plus the change in pressure from E to F. Okay, now that gives me the pressure at F. I'm not going to draw the brackets here because, well, I'll do it one last time. Okay, it's going to get a little confusing. But that gives me the pressure at F. Okay, so if I stop there, I could write equals point F, but we're not going to do that. Okay, and then I'm going to go up from F to point G plus the change in pressure from F to G. Okay, so that's going to give me the pressure at point G. All right, and then I'm going to do the pressure from G to A plus the change in pressure from G to A. Okay, and if I do all of that, okay, that gives me the pressure at point A. Now, hopefully at this point you're going, oh my Lord, this looks totally annoying. It is totally annoying. And luckily, we're not going to have to do this again and again. In fact, I highly recommend that you never do this, but I'm doing this to demonstrate what happens here, okay? So what we want to remember here is from the hydrostatic law, okay, the change in pressure, okay, assuming a constant gamma, equals negative gamma change in elevation. Okay, so this is going to make this a lot easier because if there is no change in elevation between 2 points, then there is no pressure change. Okay, so if this is 0, then this is 0. Okay, so that means right off the bat I can say, well, from D to E, look at that, no pressure change. Okay, from G to A, no elevation change, no pressure change. Okay, so these go away. So G to A, 0. D to E, 0. Okay, so already things have gotten a lot easier. All right, next, I want to think about, well, so this means that the key to figuring out my change in pressures for all these other ones is knowing this delta Z. So I need to know the delta Z's, right? So from C to D, well, let's see, we went some distance, let's call it capital H. Okay, so I'm going to go ahead and start plugging in using that capital H. So I got PC plus, okay, this is going to be negative gamma. In this case, the delta Z, we went down negative H. Okay, plus, so that's this term expanded. Okay, now I want to go E to F. E to F. I went up. So this is going to be negative gamma. And now we went up like that. Okay, so that's an expansion of this. And then from F to G, plus F to G. So we're going to do, it's going to be negative gamma. Okay, again, I'm just plugging this in. And then the change in height from F to G is going to be positive lowercase h, okay, from right here. Okay, and that equals PA. Okay, now I think hopefully you'll notice right here that this capital H, which we have no idea what it is, it wasn't given us to in the problem, we just kind of made it up. But notice that this term and this term are the same. Okay, so okay. And in fact, this you should have actually been able to guess, because if we think about this fluid right from the beginning, from point C, I could have gone straight to F, because I could have said, well, you know what? F and C are at the same elevation in the same fluid. So I could have just said, well, you know what? Maybe I went down right here in this fluid, but I came right back up that same amount. So those are going to cancel each other out. Okay, I mean, you think about a swimming pool. If you're in the deep end and you swim down a foot and then you swim over to the shallow end and then you swim back up a foot, you're going to have the same pressure as before. Okay, as long as you came up or went down the same amount, you know, if you're the same elevation, it doesn't matter. All right, so now we've got a little bit of algebra to do. So we end up with, let's see here, negative gamma H equals PA minus PC. Okay, and you could call that done, but it's not done. The last thing we need to do here is we need to recognize that PC is attached to the atmosphere. So we're going to make PC PATM. Okay, and I don't like to deal with the atmospheric pressure, so I'm going to make this 0 so that my whole problem can be in gauge pressure. So PA, the pressure at A, is negative gamma H. Okay, and if you remember from the beginning, I told you that I knew we were going to have negative pressure, and I knew that we were going to have negative pressure because this elevation right here was below the elevation of A. Okay, so now I'm going to do this problem again, but I'm going to do it in a way that's a lot faster for me. Okay, and I'm going to do this, I'm going to use yellow. Okay, and so what I want to do here is I want to start, okay, I'm going to start at point C. Point C. I'm going to note that when I go down in a fluid, the pressure increases. when I go up in a fluid. So if you'll notice here, you know, I was going from C to D. I went downward in a fluid, and it was a negative times a negative makes it positive. It increases the pressure. If I go up in a fluid, okay, let's start a list over here. Okay, if elevation increases, okay, then the pressure decreases. Okay, and vice versa. So I'm not going to write that twice. But if elevation goes down, then the pressure increases. Okay, and what I kind of think of this in my head as the swimming pool thing. Okay, and you should always just think about that. If I'm in a swimming pool and I swim downwards in the pool, I'm going to feel more pressure on my head, or whatever. All right. So anyway, so everywhere in this problem where we went downwards, so here we went downwards, okay, the pressure increased. Everywhere we went back upwards, here and here, okay, the pressure decreased. Okay, both of those had negative signs. Okay. If you go horizontal, okay, then there's no pressure change. Okay, so those terms went away. All right, so what I'm going to do then is I'm not going to even consider any movements through a fluid that don't change the elevation. Okay, so I'm going to start at C, point C. Actually, I guess I'm going to need yet another color. Okay, and I'm going to note that point C and point F are at the same elevation in the same fluid, so I can go from C to F and I'm at the same pressure. So I can just ignore all of those terms. And then I'm going to go from F to G, and look, I'm going upwards in a fluid. So I know, since I'm going upwards in a fluid, that my pressure is going to decrease. Well, how much? Gamma times, okay, now this is the hydrostatic law right up here, gamma times the height difference, okay, so that's H, boom, okay, and that gets me to the same elevation as A, so now I'm not going to worry about that until I get to A, okay, equals P at A. Okay, now notice this is the exact same thing we had right here, okay, and all I need to do is turn this PC into a 0 for gauge, and I get the same answer. Okay, much faster. All right, so let's go over here and let's do a multiple fluid type. All right, so here is kind of a multi-fluid manometer. This is it's another YouTube manometer. Oh, well, let's, all right, so I didn't quite show it all to you. I was talking to myself, I think. All right, so anyway, we've got two fluids. Fluid 1, which is over here, it's in red, or if you're colorblind, it's got these, what do you call it? The diagonals going up and to the right, and then we've got a blue fluid over here, and the blue fluid got diagonals down into the left, or down into the right. Okay, so the idea here is that we've got two fluids, and the goal here is to take advantage of the higher gamma, usually in this other fluid. Okay, because as I was mentioning earlier, if you've got mercury, which is really, really, really dense, you don't need nearly as massive a distances to use these manometers. So again, the question here is, what is the pressure at A? Okay, and so what we're going to do is we're going to build this equation. Okay, and I'm going to do it just like last time. Okay, I'm going to start at the far end, pressure at D. Okay, and I'm going to note that the pressure increases as I go from D to C by an amount change in pressure from D to C. Again, I'm not normally going to write all this out, but I'm just doing it right now because this is the first time you've seen this. And then I'm going to go from C to B. Okay, add the pressure change from C to B. And then I'm going to add the pressure change from B to A. And I'm going to go equals. Okay, so that's going to get me all the way to point A. Okay. I highly recommend that, I recommend this way of doing it if it helps you. Okay, I'm not going to do it over and over and over again. At some point, you're going to have to graduate from it because it's just going to take too long. But if you do it enough times, you still start seeing what's going on here. Okay, so first I'm going to start with pressure at D, which I'm going to note that we're just going to make that atmospheric. So I'm going to make that 0 gauge. Okay, and that means that the pressure at A is going to be a gauge pressure. Okay, so it's just going to tell us how high it is above atmospheric. Okay, so then the next thing, all right, so then from D to C, I guess I can't really use blue, let's use green. Okay, so we've got 0 plus. Okay, from D to C, I'm going downwards in a fluid. So as we go downwards in a fluid, that's a positive sign because the pressure is increasing. Think about it, a pool. And it's going to increase by an amount gamma times H2. Okay, because the change in pressure is negative gamma times the change in Z. Okay, so we always need to remember that. Okay, except I'm going to, down here, I'm going to take care of the negative sign on my own. Okay, I'm just going to think about it instead of, doing it mathematically. All right, so then I'm going to go from C to B. Notice from C to B, okay, I haven't changed fluids. And so gamma is constant because I haven't changed fluids. And that's why I'm stopping at B. It's because at B, I'm going to hit another fluid. And then the delta Z is 0. So the pressure from C to B does not change. Okay, 0. Okay, plus 0. Okay, and now I'm going to do from the change in pressure from B to A. Well, I go from B, up here the pressure changes, and then nothing to here. Okay, but I note that I went upwards in the fluid, so it's going to have a negative sign. Okay, think of the pool rule. When you're in a pool, if you come higher in the pool, the pressure is going to decrease. Okay, and how much did I go up? Well, I went up, so gamma of, this is gamma 1. I should note that this is gamma 2. Okay, it depends on the fluid. Okay, and then for this spot right here, I went up gamma 1 times H1. Okay, and then that gets me to pressure at A. Okay. Now, to expand this, that really could be the answer. I could, just kind of flip the sides here, and I could say PA equals, looks like gamma 2 H2 minus gamma 1 H1, and that is absolutely true. However, a lot of times, depending on how the problem is given to you, you might want to rewrite this as S2 gamma water H2 minus S1 gamma water H1. Okay, so where S is the specific gravity of the fluid, and gamma W is the gamma of water. Okay, so in both of these cases, so a lot of times what will happen is they will just tell you the specific weight of the fluid. So they might say, oh, this is mercury, so then this is 13.6. Okay, and then gamma water, you'll know, just because you will have done this an awful lot of times. So it's either 9810 newtons per meter cubed, or it's 62.4 PCF, okay, pounds per cubic foot. So, and that's just something that happens in a lot of problems. So just be aware that usually you're given this and not this, but sometimes you'll be given this. Okay, but if you're just given the specific gravity, then you need to know this, and you need to know how to use the specific gravity. Okay, so that's a YouTube manometer, and let's see what we can do here. All right, so let's work one that's more similar, I think, to the sorts of things that we might see. I don't know, you could see this on a test or something like that. I could easily imagine asking something like this. All right, so here's an example problem. Okay, and we are given, if I can get this to sit where I'd like it to sit. Okay, we are given that, this weird little diagram that I just drew. Okay, and so basically it looks like there's 4 fluids in this problem. So there's air, which is a fluid, and it's at 50 kilopascals, and that is sitting on top of oil. Note that this air is enclosed. Okay, you should always assume that this is a gauge pressure. Okay, always assume, which means it's 50 kPa higher than the atmospheric pressure. So the atmospheric pressure is 101.325 kPa, give or take depending on the day. But so this one is, in absolute terms, it's 101.325 plus 50, so it's 151.325 kPa. All right, anyway, so then we've got some oil sitting on top of that. It's got a specific gravity of 0.85, which means that is 85% as dense as water, which is why it sits on top of the water. Okay, if it was more dense than the water, it would sink. Okay, and then we've got some water. Oh, we need something here. Let's make this 3 meters. Okay, obviously I know it's not drawn to scale. We'll do the best we can. Okay, and then the water is attached to a manometer, and the manometer has mercury in it, and the mercury is being driven upwards to this point right here. Okay, and so the question is, how high is the mercury going to be driven? Okay, and the thing is, I have no earthly idea. Okay, you can't just look at this and know. So what we're going to do here is we're going to build our equation. Okay, that's how we solve these. We build an equation. Okay, so some of you, what I recommend is you look through that FE equation sheet, and there will be an equation for manometer. And what happens to me every year on my tests is I give somebody a question, and they look through that sheet and they find the equation, and they just use that equation. But the thing is, all the manometers are built differently, so that equation only works for a very specific manometer. It's probably a very common manometer that happens out in the world, but that doesn't really matter, okay? Because if it's not the one that's on your test, it's not going to work. So don't go looking for just a random manometer equation. You need to be able to create this equation. So I'm going to start at this point A, and I'm going to work from there all the way to the atmosphere. Okay, you could start at the atmosphere and work all your way to A. It doesn't really matter, okay? But I'm just doing it this way. I don't really know why, okay? There's no better or worse way, okay? PA. Okay, now we're going to go from A to a point B by adding the change in pressure from A to B. And then I'm going to go to point C plus the change in pressure from B to C. And then I'm going to go from C to this point right here, which is D, plus the change in pressure from C to D. Noticing I have to go to these what do they call these? The surfaces between these fluids, because it is at that point where the specific weight of the fluid changes. So my hydrostatic law, well, either I'd have to do it differential way, which no one here wants to do, or I have to stop when I get to the meniscus or the surfaces of those fluids. Okay, so then once I'm at D, I note that I don't need to go from D to E here, because that's just going horizontal in the same fluid, technically going down and then back up. Okay, but I'm going to go from D to, let's call this E. Okay, plus the pressure, change in pressure from D to E equals. Okay, now I'm going to get, that gives me the pressure at E. Okay, and that's how we build this equation. Okay, now obviously we can't solve that equation. It's not really doing us any good until we start plugging in some things. The nice thing here is that we have, we ignored all of our lateral movement. So we didn't worry about when we were going left or right, okay? Which we did really in two locations. We did it right here, and we did it right down where I wrote Hg, okay, Hg for mercury, okay? So what we're gonna do here is I'm gonna say, okay, well, PA, okay, I went from A to B. It was going downwards, so the pressure is going to increase by an amount gamma of air times the length that we went down, which in this case is 2 meters. 2 meters. Okay? Then we're going to go from, so now we're on, so that's pressure from A to B. Now we're going to change pressure from B to C. So again, we're going downwards in a fluid, so we're going to add, and it looks like we went down gamma of oil, okay, times 4 meters, okay? Now to go from C to D, we're going down, so I'm going to put a plus sign, okay? And it's going to be gamma of water times the distance we went downwards, 3.5 meters. Okay, hopefully you're starting to see the pattern here. Okay, then to go from D to E, we were all in the same fluid there, but we went upwards, minus, okay, the gamma of mercury times, how much did we go up? Well, we don't know. That's what we're looking for, Hg. Okay, so that's that one, equals the pressure at E. The pressure at E is the pressure at atmosphere, okay, which I'm going to make 0 because I'm going to work in gauge, okay, 0 gauge. Okay, and I'm going to continue to say that as long as I remember Eventually, I'm going to stop saying that, so you need to internalize that before I stop saying it. I guess that's a little rude, but I'm just going to try to keep saying it as much as possible. All right, so anyway, so now we kind of getting down to some algebra here. We're not all the way there yet. Okay, so the pressure at A, we know, so I could plug that in if I wanted to. I'm going to leave it like this for one more row, though, just because I want to. Okay, so the gamma of air. What is the gamma of air? Okay, that's the specific weight of air. And the way that we're always going to solve these is we're going to use the only gamma that we're going to be given usually is going to be that of water. It's not always the case, but usually. So this one we know, and we don't know these other ones. So the gamma of air, we're going to do the specific gravity of air times the gamma of water times 2 meters. So basically I'm going to expand the gamma like this. Okay, and I'm going to do that for all of these. So for this one, it's going to be the specific gravity of oil times the gamma of water times 4 meters. Okay, and then for this one, well, we know gamma of water, okay, times 3.5 meters. Okay, and then I'm going to expand mercury by saying SHG, the gamma of water, HHG, okay, equals 0. Okay, so I've expanded all of these unknown specific weights by just saying, well, you know, the specific weight of that substance is equal to the specific gravity of that substance times the gamma of water. Okay? So now we're basically ready to solve this because we know all of these things. I will note that the specific gravity of air was not given. So I will note for this problem, because I have one more point to make before we get into it, it is approximately, it is like this, approximately. Okay, that's of air. Okay, you'll note that that's a pretty small number, as you would imagine it would be, right? So air is about 1/1000th as dense as water. Okay, pretty pretty non-dense. Okay, so I'm making a point here with this. So let's go ahead and plug some things in. So the pressure of the air at the top is 50 kPa. So I'm going to do 50,000 PA. Okay, newtons per meter squared. Plus the S air, 0.0001225. Okay, times the gamma of water, which, well, we have to think about what system of units we're working with. Okay, so gamma of water, you're going to have to know this, is either 62.4 pounds per cubic foot, or it is 9810 newtons per meter cubed. Okay, so in this case, we're using pascals, so we want 9810 newtons per meter cubed. Okay, times 2 meters. Whew, it's a lot of mess. It's a lot of mess. One thing I will note is that you can make your life a lot easier with this a lot of times by noting that the gamma of water is in all of these terms, and so you can pull that out, so you don't have to write it a million times. But we're just gonna keep rolling on. Okay, so that's this term. Okay, expanded. Okay, plus S oil, 0.85. Okay, times the gamma of water, 9810 newtons per meter cubed. Okay, times 4 meters. Okay, so that's this term. Okay, plus gamma of water, 9810 newtons per meter cubed, times 3.5 meters. Okay, we're getting pretty long here. That's this term. Okay, minus SHG, which is given in the problem as 13.6. Okay, times the gamma of water, which is 9810 newtons per meter cubed, times HHG equals 0. Okay, so this is a big, nasty thing. Okay, so let's go ahead and I guess since I'm doing arrows, let's put that last arrow in there. So now I'm going to go ahead and I'm going to use my calculator and I'm going to get what all these terms are. All right, so if I plug all those terms into my calculator and I keep 5 significant digits on all of them, I want you to notice something here, okay? And This is going to be where you start to kind of think more like an engineer, or you start to kind of get some intuition here. Which one of these terms basically doesn't matter? Okay, so if we zoom in a little bit, I don't know how well y'all can see this on YouTube. Okay, but look, we've got 49,000, 33,000, 50,000, 2.4035. Okay, this term is essentially irrelevant. Okay, so one of the other kind of basic rules, the things that you can do here, is that if you're in a case where there's one fluid whose specific weight or specific gravity is really, really small, so a very non-dense fluid compared to all the others, or if there's multiple fluids that, you know, have a very small specific gravity, you can ignore them, okay? The only way you couldn't ignore them is this air layer where, like, so right now it's 2 meters, and the other ones are 4 meters, 3.5 meters, 3 meters, whatever. The only way you couldn't ignore it is if there was like thousands of meters of air, okay? Which, I mean, so like, you know, you can't ignore atmospheric pressure, which comes from thousands of meters or tens of thousands of meters of air. You know, in this case, you can ignore this. So you could just go, you know what, I'm going to ignore that, okay? And that's going to go throughout this course, okay? So if you're dealing with air and water, unless there's tons and tons and tons of air compared to the amount of water, it's not really going to matter. So I'm going to ignore it in my solution. If you were to include it in your solution, that would be fine, but it's really not going to make a difference, okay? So if we solve this problem all the way, then I'm going to get Hg equals 0.88 meters. Typo. Hold on. Okay, my apologies. There was a typo there. So, or not a typo. I screwed up punching it into my calculator right here. Okay, so make that correction in your notes. Anyway, so the height of the mercury is 0.882 Hg. Okay, so let's go up here. Let's think about this. Okay, so let's think about these general rules that I was trying to make earlier. And let's write a few more. Okay, let's just try to think about this. Okay, so yeah, so the first, and this is the most important one, if the elevation goes up, the pressure goes down. Okay, so then how do we do these? Okay, so another thing we want to do is we want to be consistent. Okay, with units. Okay, and signs. Okay, and we're going to basically, the way that I do these is I'm going to kind of, quote unquote, build the equation by starting at one end, okay, and usually there's one end that you know and there's one end that you don't know, okay, and kind of like adding the change in pressure from one meniscus to the next. Meniscus to the next. Okay. Okay, always keep in mind this. Okay, the gamma of a fluid. Okay, so if I kind of number these or something. Okay, this is really important. So the gamma of a fluid is the specific weight of that fluid times the gamma of water. Okay, so just always remember that as you're working through. And then this last little thing is that, so if air is a fluid, is one of the fluids, okay, then you can usually neglect it. Neglect vertical variations in the air. Air, and why can we do that? We can do that because gamma of air is almost zero. Okay, basically it almost has no, okay, the only way you can't neglect it is if all of the fluids in the problem are gases. Okay, so then obviously then it's not small by comparison. Or there's just like, you know, the entire atmosphere of air or something like that. Okay, so let's see. Oh, one last thing I wanted to note about that problem we just did. Where is it? I think, ooh, look how huge it is. Wow. All right. Notice this 3 meters right here. We never use this. Okay. This is what they call, or what I would call. Whoa. Geez, dog. That was very shocking. Okay. You got it. Good boy. This 3 meters down at the bottom here, which for some reason will not circle, we never used. Okay, so I'm going to try to zoom in on it, if it will let me. Okay, this 3 meters right here, we never used it. Okay, and notice it's a red herring. Okay, we could go down and down and down. This tank could be infinitely deep, and it's not going to affect the pressure of the waters above it. Okay, think about like when you're, again, I always think about the swimming pool. I'm like, well, if I'm 2 feet deep in the pool, and the pool is 3 feet deep, or if the pool is 7,000 feet deep, there's no more danger of my head getting crushed by the pressure because of what's underneath it. Okay, so don't worry about this 3 meters right here. This 3 meters is just there to confuse you. Okay, I put it there because I'm a jerk. Anyway, so wow, that's a lot of spreading. I usually like to kind of stay under this white line that I create to kind of give myself some structure. Anyway, so hopefully that all made some sense to you guys. This is a relatively short lecture, so we're only at 51 minutes, so that's good. Again, take care of yourselves. Take care of each other. Let me know if I can help. That is why I'm here. So take it easy, and yeah, let me know. All right, talk to you later. Bye.